All right, so welcome to Math 150, Section 1, Multivariable Calculus 2021. This is, I think, lecture 10-ish, and we're doing the multivariable chain rule. So what's nice is we've actually already done the chain rule earlier. So we had a lecture where we talked about it, and so this is really going to be the second lecture on the subject. So before I start going into details, are there any questions, anything people wanted to speak in the class? Okay, I think this is the worst topic all semester in terms of the theory. You can, of course, just memorize the formula. It's nice to have an idea of why it's true. And so in the video, we actually went through, we did some examples. Let's let A of X equal F of G of X. And whenever you hear the word of, you should be thinking of the chain rule. And we tried special cases of F and G to build intuition. You may be, F of X equals, 2 x to the fifth plus 1, and maybe G of X is X2. This is a little bit harder than the example there, so I'll make it a little bit easier. I'll put a 2 here and a 3 here. And so if I do that, if I look at F of G of X, that's going to be F F of X squared. And so that would just be 3 x squared the fifth plus 1 is 3 x to the 10th plus 1. And I can start taking derivatives and I can try to figure out what it is. Can I differentiate this function directly? Is this a hard function to differentiate? Yeah, not a problem at all. What if I did it the other way? What if I had f of x is x squared and g of x is 3 x to the fifth plus 1? Then f of g of x would be f of 3x to the fifth plus 1. That would be 3x to the fifth plus 1 squared. Well, I can actually expand the square, that's not too bad. And that would become 9x to the 10th plus 6x to the fifth plus 1. Can we take the derivatives here directly? Yeah, not a problem. And in both cases, we see if A of x is f of g of x, A prime of x is equal to f prime at g of x times g prime of x. So again, we are building intuition. This is similar to how we build intuition for what is the derivative of a product. Do we need to do this? No. But this is the more useful skill. You will see things in life that you haven't seen before. Can you try to sniff out the relationship? Can we explore some special cases and get a sense of what's going on? We talked about how to generalize. And generalizing this to several variables becomes a little bit of a trick. And so the first thing we looked at was, let's say we had A of t was f of g of t. Where maybe f G took a real input and gave us a triple as an output. F took a triple as input and gave us a real number as output. So if you want, you could think of maybe G of t as x of t, y of t, z of t. Some nice triple like that. And when we went through, we used the definition of the derivative. Which of the many definitions of the derivative did we use? For multivariable calculus, which was the definition that was useful? So you should know that this is what we keep using again and again in multivariable calculus. Which limit? Three different formulations from Calc 1. One of the three generalizes nicely to multivariable calculus. Okay, the first was the limit as h goes to 0. The second was the limit as x goes to a. And the third was subtracting off the tangent line approximation. Which is the one that generalizes nicely to multivariable calculus? Not the limit as h goes to 0. The tangent line is that we saw that what it really means for a function to be differentiable is that the tangent line does a great job. If this is my function, to be differentiable at this point means that straight line does a phenomenal job locally. And then when I zoom in, the function essentially looks like a straight line. And when we generalize it to multivariable calculus, we then do the tangent plane. We would do f of g of t plus h is basically f of g of t plus the gradient of f at g of t dotted with c of t plus h minus c of t. And this is where we were. This is how fast the function is changing at the point, and this is how much we've moved. And when we do the dot product, it gives us df dx times the amount of movement in x, and then df dy plus times the amount of movement in y. And so this leads to dA dt was df dx at g of t times dx dt plus the dot plus df dz dz dt, and this is of course at g of t, and this is at t. So this is what we had last time when we were doing the chain. We could have, instead of writing partial x, partial t, we could have just put in dx dt, regular d from Calc 1, because x is only a function of 3. And we got this by looking at, c of t plus h minus c of t divided by h times h, we multiplied by 1. And then when we looked at the component, the first component became x of t plus h minus x of t over h, blah, blah, times h. And you can see this is becoming dx dt. So this is how we take the partial derivative of a function a with respect to the variable t. And again, this is a little bit of a special case because a depends on only one variable. What if a depended on several variables? So over here, g is depending just on one variable. Maybe instead of having one variable, we have two variables. We might want to use polar coordinates and go back and forth between polar and Cartesian. And so it's a little bit limiting to only have one input. But what's nice is that essentially the same argument is just going to propagate through. If I wanted to, could I have just pretended for the whole time that, oh, I'm sorry, I'm using C here. What should I be using instead of C? I'm basically calling C of T just G of T. My curve, I'm doing the curve in space. And so in the special case when I only have one variable, I sometimes like to just write C of T to remind myself it's tracing out my curve in space. But this is really the point G of T. G of T plus H minus G of T. If G depended on more than one variable, but I'm only changing T, notice that the calculation is essentially the same. When I get to C of T plus H minus C of T, or G of T plus H minus G of T, all that changes now is these things have more parameters. So now, let's extend. Let's have G from R2 to R3 and F from R3 to R1. And so now we would have maybe A of UV is F of G of UV. And it's going to be essentially the same calculation as before. So again, we use the tangent plane approximation. And we'll have F of G of U plus H V should be approximately F of G of UV, where I stop, plus the gradient of F at the point G of UV, dotted with G of U plus H V minus G of UV. It's essentially the same calculation as before. And now, what is this quantity over here? Well, this is going to be X of U plus H V minus X of UV over H for the first component, second component, third component, and H. So I've just done a very similar calculation before. I multiplied by 1 by H over H. And essentially just V is along for the ride. It's just following along. Now that V is here, I can't write normal dx dt or normal dx du because I have more than one variable. And now using those partial symbols is much better. It's never wrong to use the partial symbol. If you only have one variable, is it a little bit of an overkill? Yes. If you only have one variable, which is the one that's varying? Well, one variable. If you have more than one variable, then you have freedom as to which one is moving. And then you really need to say partial. So over here, this would just become, in the limit of H goes to 0, partial X, partial U at the point UV. So this is the theory. So before I erase it, I want to make sure everybody's comfortable with the theory. It's essentially the same theory we had before. We just have another variable along for the ride, and we just do things component by component. So a general principle in mathematics is whenever you're given a really hard problem, basically avoid it like the plague if you can, and do a lot of simple problems and then piece them together. I would much rather do a lot of simple problems than one more involved all at once. And so here we've done the simple problem. We started with a one variable chain rule. Then we said, well, what if we generalize and a little bit more? And we used the tangent plane approximation. And we were careful, we wrote it like this because we had an idea of what was coming down the road. So we knew there was going to be more things there. And then in the limit, this piece over here, the x of c plus h minus x of c over h times h, that just converges to dx. And now when we have more variables at play, all that happens now is that we have partial x, partial u. We have to do with that. So in general, we can write down what the instance is. You always want to decide what are you using as your variables for f, what are you using as your variables for g. And you always want to write it as f of g of. Don't get lazy. The book often drops that intermediate step of that g inside. I like to put it there to just really remind myself where things are. Let's say we have g from R2 to R3. We have f from R3. We have a of uv is f of g of uv. You can view this as f of x of uv, y of uv, v of uv. So this part over here is my g of uv. You give me a pure uv, this gives me a triple. I prefer to write it like that rather than just writing f of x of uv, y of uv, z of uv, because when I write it like this, I don't have f of g of. I have f of a triple. And so now, I want to take the derivative of a. How can I take the derivative of a? What are the options? Okay, what partial derivatives of a can I do? I can do u of a. So I have dA is the gradient of a, is grad a, all these are the same notation, is dA du, dA du. So a is a function of two variables. So its derivative is going to be a pair of numbers. If a was a function of 5 variables, how many components would I have? I would have 5. And so now I just want to figure out what dA du is and then dA dv. And they're going to be very similar to what just done before. So dA du is dx dx at my point d of dv times dx du at the point dv plus df dy at g of dv dy du plus df dv at the point g of dv dv du, and of course this is at the point dv. And then partial of a with respect to v is something similar. So this is the chain. Can I cancel the dx's? No. If you could, is that just saying dA du is just df du? Well, again, remember, a is not the same as f. A is f evaluated at g of dv. So we don't expect the partial of a with respect to u to be the same as the partial of f with respect to u. And I've deliberately chosen it like this because f needs 3 inputs and a only needs 2 inputs. A is from R2 to R. F is from R3 to R. So a is from R2 to R. So I don't expect df dA, I'm sorry, df du and dA du to be the same because I can't even talk about df du. F needs 3 inputs. But if you think about it, the derivative of a with respect to u is the derivative of f with respect to x times the derivative of x with respect to u, plus the derivative of f with respect to y times the derivative of y with respect to u, plus the derivative of f with respect to z times the derivative of z with respect to u. So the formula isn't too bad. We just have to calculate all these different pieces. Sometimes you can avoid doing this by just substituting everything in and getting a monster function of u and v, and then just differentiating that directly. Other times it's more convenient to just calculate these derivatives and then substitute them. If you can do both, and they're both equal, does that mean you made no mistake? No. It's sad, but you could actually have made the same mistake or an equivalent mistake on the two. What if the two calculations are different? There's something wrong with at least one of them, but at least one of them is wrong. I remember when I was in high school, I took a physics class at Harvard, and as a real man, I have no complaint that Yale didn't consider that a real class. But I remember on one of the physics questions, I actually got full credit for the problem, even though I made 2 mistakes in the calculation. The 2 mistakes actually canceled. I was off by the sign. But because I had to do that an even number of times, everything canceled out. I had the right answer. How do you think they graded this problem? Do you think the graders carefully checked every single line? Or what do you think they did? Yeah, the answer right. And if it's a complicated answer and it's right, then almost surely they must have done all the correct ones together. When you're designing questions, you want to try to design questions such that this won't happen. In integration by parts, it's the integral of uv minus the integral of v to u. frequently the UV term is 0. You often have functions with the UV boundary term vanishes. And if you have to do it twice, you drop the minus sign, that's going to go away. You want to be careful. Just because you have the correct answer does not mean you've done the correct calculation. It gives you some confidence. And if you can do a problem multiple ways, that's great. So I think one of the problems, and I might have it a little bit off in the video, was that A of theta. And so f of xy is going to be x cosine x squared plus y. I think this was the example in the video. And of course, if you look at f of g of r theta, where g of r theta is going to be x of r theta, y of r theta. So what should I choose for x of r theta? What is x as a function of r and theta? What kind of coordinates are we using? When you see r and theta, what should you be thinking? Sorry? Polar. So how would you write x in polar coordinates? You need to know the polar coordinates, the cylindrical coordinates, the spherical coordinates. So x should just be r cosine theta. And what should y be? I'm sorry? What? Sine theta. And this just comes from, if I have a point here, x comma y, this is r, this is theta, so this is r cosine theta, and this over here is r sine theta. So instead of studying this function as a function of x and y, I could study it as a function of r and theta. So what would f of g of r theta be? What does x become? This is just f of r cosine theta, r sine theta. So what would the x over here become? It would just be r cosine theta. And then we would have times the cosine of x squared plus y squared. Well, what's x squared plus y squared? Not 1.
Oh, sorry.
Yeah. So what's x squared plus y squared? R squared. Yeah. Because x squared is r squared cosine squared theta. Y squared is r squared sine squared theta. So my function is just r cosine theta times cosine r squared. So if I look at the function a of r theta, it's just a function r cosine theta times cosine of r. Do I need to do the chain rule to figure out the derivative of this? No, I can take the derivative directly. So what would be, do you want to take the derivative with respect to r or with respect to theta? One of them is easier than the other. Yeah, theta only occurs once as cosine of theta. R occurs as r and cosine of r squared. So if I do dA d theta, the derivative of cosine is minus sine, would be minus r sine of theta times cosine of r squared. If I do partial a partial of r, well, I can pull out the cosine of theta, right? And now I just have to take the derivative of r cosine r squared with respect to r. Well, the derivative of r with respect to r is 1, so it's going to be cosine of r squared plus r times the derivative of cosine of r squared. Derivative of cosine of r squared is going to be negative sine of r squared times the derivative of r squared, which is 2r. It should be minus 2r squared sine r squared, if I've done it correctly. So does it look like I have done the calculation correctly? Yes. Yes. We have a product. So if I have a product, let's call it, I'm running out of letters, b of x, c of x. And I want the derivative of this using the product. So I might have actually drawn, so it's going to be b prime of x and c of x plus b of x and c prime of x. And let's, instead of using x, since we're doing things with respect to r, let's make all of these r. So if you're ever not sure about how to do a derivative, it's actually not bad to just write things out slowly like this and don't skip any steps. So here's my product rule. Let's let b of r equal r, b of r is cosine of r squared. B prime of r is 1. C prime of r is cosine is negative sine. And I have the derivative of r squared, which is 2r, which I just put up in the front. Because it's b of r times c prime of r. So now I substitute b prime of r, c of r is going to be 1 times cosine of r squared. Now I have plus b of r, c prime, that's these two. So it's going to be r times negative 2r with minus 2r squared sine r squared. So did I get the problem right? Okay, good. I've been doing this longer. I've been teaching this class longer than you've been alive. I should be able to do this quickly without going through all the steps. Is it a bad idea to put in all the steps? Not at all. If you're not confident on your speed, by all means, please put in the steps, go through it very slowly and methodically. The more involved the derivative is, the more of these expressions you might have. What if C was a composition? Then I would have C prime, and I would have a little holding path. I would have C prime over here, and I would calculate with that. What if C of R was, D of R over E of R? How would I calculate the derivative of C prime? Using the quotient rule. So over here, I wouldn't have anything here yet. I would have this blank. I would have this part. I would know this part. I would know this part. I would know C prime. I need to compute. And then I would come over here and say, okay, well, C prime of R is going to be C prime of R, C of R minus D of R, C prime of R over E of R squared. And then I would have to write down what's D prime, what's D prime, and substitute. And just the more things you have, the longer it gets. But you keep breaking it up into steps. Yeah.
Right.
Which cosine theta? This one over here?
Yeah.
Well, it's because we have dA, we have a cosine theta. This has no R dependence. When I take the derivative with respect to R, this is just a constant. So I might as well just pull this outside and just consider the function R cosine R squared. And so if I consider the function R cosine R squared, that's what I have here, R cosine R squared. Okay. Any other questions on this? So one way that I was able to hopefully convince you that I know my calculus is I wrote more steps. How else could I convince you that this is the right derivative? Well, at least provide some more evidence to convince you that this is correct. Yes, how can I do this a different way? Yes, For some strange reason, that hasn't been erased from the board yet. It's hovering, right? Why not use the chain rule for this problem? If you had your choice, would you choose to use the chain rule for this problem? Not unless you are going through some real issues and you just feel the need to just be, maybe it's therapeutic to just do lots and lots of derivatives. The chain rule is going to be much worse for this problem because I can substitute directly and I can get a nice function. But there will be other problems later on that are more involved where it is better to use the chain rule. And so let's do the chain rule. And we'll do it slowly. So we have VAVR is going to be df dx dx dr plus df dy dy dx. I am doing a slight review. I'm not writing where I evaluate f df dx df dy. Is it understood where I'm evaluating? I'm always evaluating this at my g of r theta. So these are at g of r theta, others at r theta. And again, this is just convenience in terms of just how much I'm writing. My right arm is already beginning to hurt. And I know I have another lecture to go later, so I'm trying to conserve strength. It's also, at some point, you have so much stuff on the page, it gets harder to see what's going on because there's so many things. So if you can understand that you always evaluate this at g of r theta, then we don't need to put that in and we can save a little bit of space. If you're unsure, and it helps, put it in. So let's start calculating derivatives. So if x equals r cosine theta, what is dx dr? It's just going to be, it's just going to be cosine theta. And if y equals r sine theta, what's dy dr going to be? Something. So this is nice. We already have two of the pieces we need. We now need to calculate the other two. And this is where it would be nice if this was pre-COVID and we could use all the different boards and not be compressed. But we really want to keep that up. So we know f of xy is x cosine x squared plus y squared. Which do you think is the easier derivative to do? The derivative with respect to x or the derivative with respect to y? Why? Because it doesn't have that other x component. So there's an asymmetry. If I had xy times cosine x squared plus y squared, then if I take the derivative with respect to x, I could play the game of switch the roles of x and y, and I would have the other derivative here. But there's an asymmetry. This is going to start to get deep. df dx. So I first take the derivative with respect to x, so I have to use the product rule. So the safe state, the derivative of x is 1 times cosine x squared plus y squared. Plus x times the derivative of this piece. Right? And the derivative of this piece, the derivative of cosine is going to become minus sine. So minus x sine x squared plus y squared. But now I have to take the derivative of x squared plus y squared with respect to x. What do I get? 2x. We get a minus 2x squared. That's df dx. Do I want to evaluate df dx at point x, y? Where do I want to evaluate df dx? Sorry? G of r theta. I want to evaluate df dx at the point G of r theta. So that means take x to be r cosine theta, take y to be r sine theta. So this is going to become cosine squared, cosine of r squared, minus 2x squared. So it's going to become 2r squared cosine squared theta. And we'll have sine of x squared plus y squared. So it'll be times the sine of r squared. Okay. Now, what do we have to do next? df dy. So df dy is going to be a little bit easier because when I take the derivative of this with respect to y, the x doesn't matter. The x is just a 1 to the y. So this is going to become x. So the cosine becomes minus sine x squared plus y squared. And when I take the derivative of this with respect to y, I get 2y. It's going to be minus 2xy sine x squared plus y squared. So df dy at g of r theta is going to be substituting in negative 2xy, negative 2r squared cosine theta, sine theta, sine of r squared. All right, if you look at it, we basically have everything we need. We have df dx at g of r theta right here. Df dy g of r theta over here. We have dx dr at r theta right here. We have dy dr over here. What do we have to do? Put it all together. And so now, at this point, I think I can now finally erase the chain rule because we've used it. It stayed up a long time. We need the board state. At this point, if anybody is preferring to use the chain rule for this problem, you have mathematical issues. Okay, and we need to talk, we need to do an intervention, we need to do it. Okay, it's exploding out of control here. Right? So let's just start substituting in. So the first is we have df dx at the point g of r theta. So we have cosine r squared minus 2r squared cosine squared theta sine of r squared. And what do we multiply this by? Multiply this by cosine theta? Yes? And then the nightmare continues with df dy, which is going to be minus 2r squared cosine theta sine theta sine of r squared. What do we multiply that by? Sine theta. All right, let's start playing the simplification game. So the first piece is going to become cosine theta cosine r squared. The next piece is minus 2r squared cosine theta cosine squared theta sine of r squared. How else could you have written cosine theta cosine squared theta? You could have written it as cosine cubed theta. Anybody know why I'm not writing it as cosine cubed theta? Yeah, this term also has a cosine theta. And so I know this term has a cosine theta, so I'm leaving one cosine theta piece of the factor. And then continuing over here, you have a minus 2r squared cosine theta sine squared theta sine of r squared. Oh, look, they both have a 2r squared cosine theta. right? So this is just equal to cosine theta cosine r squared minus 2r squared cosine theta. Now, oh, they also have a sine r squared. That's great. I can factor that out as well. And then I've got cosine squared theta plus sine squared theta. What's cosine squared theta plus sine squared theta? 1. And if we look up top, cosine theta times cosine r squared, yeah, minus cosine theta times 2r squared sine r squared, yeah. It actually matches. So hands down, this is a problem where it is better to do it directly and you substitute in than to go and use the chain rule. For a lot of things, theoretically, the chain rule is useful. For some problems, we happen to have nice forms for these. This is better than having a really complicated compound function. You know, I deliberately wanted to choose a painful problem to just go through the steps very carefully. And you have beautiful formula which sadly was finally erased. That's how you attack all these problems. Just do it very slowly, write down what everything is. The ADR is df dx, dx dr plus df dy, dy dr. And then what is df dx? What is df dy? What is dx dr? What is dx? What is dy dr? If you have all of those individual pieces, you can then put them together. Any questions on this problem? Yes. I would have to think it through. There's some really strange things where I can't put them in. It might be the case where someone is giving you information, not giving you exactly what the functions are. They're just telling you at this moment in time, dx dr is 3 and dy dr is 5. They might be giving you information like that without actually telling you the full function. So sometimes they talk about, you have maybe a balloon that's expanding and they want to know how the volume is changing at a given moment in time, where the radius is now changing at this rate. So you may not know what the radius is as a function of time in general, but you may know that at this instant in time, it's increasing at 2 meters per second, which would be an extremely fast expansion for the balloon. And so if you have information like that, you can't just do the direct substitution. You have to be using the information that's provided. Yes. Well, but remember, we have cosine theta multiplying the thing in brackets. So it's nice that we were finally able to get a bracket reference into today's lecture. And so when you multiply that out, I could pull out the cosine theta from both of those sides. Yep. Yep. So it all works out in the end. Any questions on this? So let me just end with doing an integration by parts. Let's integrate from 0 to 1 x cosine of x. So if I happen to know an antiderivative for x cosine of x, I'm in great shape. Unfortunately, I don't know an antiderivative for x cosine of x. So the formula for integration by parts is equal from 0 to 1 of u dv is equal to uv at 0, 1 minus u equal from 0 to 1 of dv. And let's just go through this very slowly. Here, u equals dv equals u equals dv. In most problems, there's really only 2 possible choices. And when I'm looking at the 2 possible choices, one of them is u, one of them is dv. What are the 2 possible choices for u? X and cosine of x. If you try a choice and it's not working, what do? Just like pushing the wall in disgust? Try the other, right? Not a big deal. If it's not working, put the piece of paper aside, try the other one. What if that doesn't work? Then you hit the wall. Or you go back to the first one and say, oh, maybe that wasn't so bad after all. So here, do you think you want the u to be x, or do you think you want the v to be? If the u is x, when we take the derivative, its degree goes down. If the dv is x, when we take its integral, its degree goes up. Are we trying to get the power of x higher in this expression or lower? Lower. So where do you want to put the x? With the u. And again, if you can't figure that out, there's fortunately only two choices. So we take u to be x, so du is just going to become 0. dv is cosine of x dx. I like to write the dx. So what function has the root of cosine? Just the sine of x. And now note I have all of my things here. I can just directly substitute. U dv is equal to uv. So it's going to be x sine of x at 0, 1 minus the integral from 0 to 1 of v du sine of x dx. Well, this isn't so bad. When x equals 1, we have 1 sine 1. So this is just the sine of 1. And then when x equals 0, we just have 0. And now we have the integral of sine of x. What function has derivative sine of x? Negative cosine. So actually, if you want, I can use this as negative sine of x. And what function has derivative negative sine of x? Cosine. So this is just going to be cosine of x at 0. So it would just be the sine of 1 plus the cosine of 1 minus the cosine of 0. And this is how you would do the integration by column. Any questions? So this is one of the more common integration techniques that we need to know. For the most part, this is going to be what you want to do. The only time you might have something a little bit different is if I give you something like x squared e to the negative x squared. And I want to integrate this by part. It turns out if we don't have the x squared, we have a really nice way of integrating this using polar coordinates. You might think that's a little strange because it's a one-dimensional integral, but there is a way to do this with 2 dimensions. If you want to integrate this by plots, you have to tell me what is u and what is dv. So for this problem, what would you choose for u and what would you choose for dv? So the natural thing to do is to try x squared and e to the negative x squared. The problem is if you try that, it doesn't work because we don't know a function whose derivative is e to the negative x. In what way? So the problem is we need a function whose derivative is e to the negative x squared if we're doing it like this. And there is no simple function whose derivative is e to the negative x. Okay, so what could we try if this doesn't work? We could try switching them. Well, unfortunately, if we switch them, it's hell. We have e to the negative x squared. And when we take the derivative, we'll get a negative 2x e to the negative x squared. We have an x squared. We'll have now an x cubed over 3. So now the degree of x has gone up. So if we try that, it sadly doesn't work. The solution for this problem, and this is one of the hardest integration by plots you can have, is you split the x squared. We put 1x over here, and then we have e to the negative x squared x dx. What's the derivative of x with respect to x? It's just gonna be the idea. And now this is set up to integrate nicely. This would just be negative 1/2 into the negative x squared. And so now if I try to do that, I've now decreased the power of x from x squared times x to the first. This is essentially the hardest integration by parts we have. And I just wanted to put it out there, we had a little extra time today to just alert you what is the main trick in integration by parts. Because I could be in a situation where the two natural guesses don't work. And then what you have to realize is I really have the function x e to the negative x squared. So when I'm trying to decide what is u, you could be x, you could be x squared, you could be e to the negative x squared, or it could be x times e to the negative x squared. There was another choice that I was missing. All right, this is a good place to stop.